Have you ever looked at a really complex electrical circuit with multiple voltage sources, resistors, and maybe even current sources, and felt a bit overwhelmed trying to figure out what the current flowing through just one specific component is? Well, you can calculate the load current using Thevenin's equivalent by simplifying the entire circuit, excluding the load, into a single equivalent voltage source in series with a single equivalent resistor. Once you have this Thevenin equivalent circuit, finding the current through any connected load becomes incredibly straightforward, almost like solving a simple series circuit. This powerful simplification method is known as Thevenin's theorem, named after French telegraph engineer Léon Charles Thevenin. It allows us to replace any linear to terminal circuit with a simple equivalent, making complex network analysis significantly easier. The core idea is that, from the perspective of the load, the simplified circuit behaves identically to the original complex one. Let us walk through the steps to calculate load current using this elegant approach. First, identify the load resistor where you want to find the current. Temporarily remove this load from the original circuit. This creates two open terminals. Next, you need to find the Thevenin equivalent voltage, often written as V subscript TH. This is the open circuit voltage across the terminals where you removed the load. To find V subscript TH, you might use nodal analysis, mesh analysis, or even source transformations on the remaining circuit. Remember to consider all active sources in this step. After finding V subscript TH, your next step is to calculate the Thevenin equivalent resistance, or R subscript TH. To do this, turn off all independent voltage and current sources in the original circuit. Independent voltage sources are replaced by short circuits, while independent current sources are replaced by open circuits. Any dependent sources must remain as active. Then, find the equivalent resistance looking back into the terminals where the load was removed. You might use series and parallel resistance combinations, or apply a test voltage or current source if dependent sources are present. Once you have both V subscript TH and R subscript TH, reattach your original load resistor, let us call it R subscript L, in series with R subscript TH and across V subscript TH. Now you have a very simple series circuit. The load current, I subscript L, is then calculated using Ohm's law. It is simply V subscript TH divided by the sum of R subscript TH and R subscript L. This calculation gives you the exact current that would flow through the load in the original, more complex circuit. This ability to model a complex network as a simple voltage source and resistor is not just an academic exercise. It is a fundamental concept used extensively in circuit design and troubleshooting, especially when you need to analyze how various loads will affect a particular part of a system. Knowing Thevenin's equivalent lets engineers quickly assess the voltage and current capabilities available to any connected component without reanalyzing the entire larger circuit every time the load changes. It is a powerful conceptual shortcut. Mastering Thevenin's theorem empowers you to cut through circuit complexity with precision. By systematically reducing intricate networks into a manageable equivalent, you gain a clear, reliable path to determine load currents. This skill not only simplifies your calculations, but also deepens your understanding of how different parts of an electrical system interact, ultimately making you a more confident and efficient circuit analyst.